So as we extend this, we're going to assume the same null hypothesis. We're going to assume that the offer of HLAB help has no effect on whether you win or lose your case. I wrote win versus lose. Okay. But we're going to change to make realistic, make true this time, is the sampling. So instead of assuming a simple random sample, we're going to this time correctly assume Bernoulli randomization, not simple random sampling. So if we go back to the previous slide and look at this, what's going to change? Well, there's still only 3 people in the study, and I'm still going to have the 001 for what happened to their outcomes. And it's still going to be true that the actual data I observed is TCC. What's going to change is this part. What's going to change is the list of possible ways the randomization could have come out. Because if I am flipping a coin for each person, I'm not restricted to possible results where one person has T and the other 2 have C. So let's see how that looks. So we still have our 0, 0, 1. Okay. And we still have, which way do we say it goes? We still have our TCC. And we're still going to calculate the difference. Okay, and just like before, it's the same numbers. If we do this, we'll get negative 0.5. Okay. But looking back at here, again, before, now I started to list the different ways the randomization could have come out under the assumption of a simple random sample. Now I'm going to do that, but under the assumption of flipping fair coins. So let's see. It could be that one person gets T and the other 2 get C's. We'll start by writing down the same options we had before. But it could also be the case that this time 2 people get T and 1 person gets C. And it could even be the case that all 3 people get T. Or it could be the case that all 3 people get C. I know I have all the options because there are 1, 2, 3, 4, 5, 6, 7, 8 options. And how many ways can you flip a coin 3 times? Well, there's 2 options for the first coin times 2 options for the second coin times 2 options for the third time. 2 cubed is 8. And so I know there should be 8 options here. So now I'm going to go ahead and calculate these differences. Well, I had already done this first couple, right? So this one should be 0 minus 0.5 is negative 0.5. And this one should be 1 minus 0 is 1. But now I have some new ones. So looking at this fourth one, the mean of the outcomes among those who got treatment, well, there's 2 of them. They both have zeros, so it's a 0. The mean of the outcomes among those who get control, well, there's 1 person and they got a 1. So that's going to be a negative 1. Now, next line, the mean of the outcomes among the people who got treatment, there's 2 of them. You should be doing this on your own page and see if you can do it ahead of me. See if you can finish this while I'm talking through it. There's 2 people who got treatment. The mean of their outcomes is 0.5. There's 1 who got control. Their outcome is 0, so I get a 0.5. Here, next line, I've got 2 people who got treatment. Their mean is 0.5 minus 1 who got control. I get a 0.5. Okay, I got that far. Now I'm stuck, right? Now I'm stuck because I have 3 people who got treatment and 0 who got control. So I could try to start this. I got, okay, among the people who got treatment, their outcomes were 0, 0, 1. The mean of those is a third. But now I'm going to subtract what? The mean of the outcome for the people who got control. Okay, but I don't have anybody who got control. So that's not going to work. Now, you can't just plug in a 0 there. Some people want to say, oh, 0.33 minus something, I don't know. Let me plug in a 0. But that's not right. Just because I don't know what the mean outcome is under control does not mean that the mean outcome under control should be 0, right? Like if you plug in a 0 there, if you decide this difference is 0.33 is a third, then you are assuming that anybody who got control would have lost their case. And that doesn't make any sense. Same thing here, right? If I'm trying to find this difference, if everybody got control, well, I don't have any idea what the mean outcome would be if somebody got treatment, and then I can subtract a third, but I don't really know what that difference is, right? A third minus I have no idea is I don't know, I have no idea. And so we have to cross these out. This is a flaw. This is a problem with Bernoulli sampling for non-parametric tests. This is just how it is, right? Although if you notice, if you have many more than 3 units in your study, like if you have 207 units in your study, then there will be many, many, many more rows in this table, and you'll still only have to cross out 2 of them. You just cross out those 2 and you pretend that they were never there. That's what you do. Okay, what about the rest? Here is the set of values of the test statistic under the null. So let's label these things, right? These differences, this is a test statistic. We have our null hypothesis, and this thing is the reference distribution. It's a list of all the possible values the test statistic could take on, along with their probabilities. Well, why am I saying it's along with their probabilities? Well, we can draw a picture. Under the assumption that we're flipping a coin for each unit, each of these possible ways of the randomization coming out is equally likely. So therefore, I know that 1 out of these 6 times, I would get a 1. And 1 out of these 6 times, I would get a -1. And 2 out of these 6 times, I would get a 0.5. And 2 out of these 6 times, I would get a -0.5. And this is a picture of the reference distribution of the test statistic. This is the same place I stopped in the previous slide, right? When I was doing simple random sampling, right? We have the null hypothesis, we have an assumption or some knowledge about how the units were assigned to one group or the other. We have a test statistic, and we come up with a reference distribution for that test statistic. What we're saying is, under the assumption that treatment versus control has no impact on outcomes, then here are all the different ways treatment or control could have come out. And so therefore, here are all the different possible values of the test statistic. And they're equally likely if I'm doing Bernoulli sampling with fair coins, or if I'm doing simple random sampling. Okay, now there's one more term that we didn't define. And the term that we didn't define is p-value. And I know this is a term that you've heard before. Here's what a p-value is. Let's go back and do it for the previous one, and then we'll do it for this one. The p-value is the probability you would see a difference in means at least as extreme as you actually observed. So here, the actual difference in means we saw is the one in red. That's the -0.5. So here's a 0.5. Here's a -0.5. Okay. The probability that given this study, given this null hypothesis, assuming there's no impact of an HLAB offer on whether you win your case, the probability that you would get a difference in means less than or equal to -0.5 is 2/3, right? 2/3 of the time you'd get a p-value less than or equal to 2/3. Let's go back to this one. Okay, the red -0.5 is still the value of the test statistic that we actually observed. Let me change colors to make this more clear. So here's the one I actually observed. Let me write that, actually observed. And so what I'm interested in is the probability I would have seen a value of the test statistic at least as extreme as I actually observed, assuming that the null is true, right? This distribution is only the correct distribution for the test statistic if the null is true. If offering HLAB help does have an impact on whether you win or lose, then this table I've made is just not correct, doesn't make any sense. This is only true under the null hypothesis. So here are all the cases where the difference in means is less than or equal to -0.5. Okay. So let's go to the next slide and more formally define these p-values, and we'll come back and find different kinds of p-values for this particular case. So in general, a p-value is the probability of observing a value of the test statistic that is at least as extreme as you actually observed, and then crucially, if the null hypothesis is true. Anytime you are providing or defining a p-value, you have to remember this piece, if the null hypothesis is true, because the p-value only makes sense under the assumption that the null hypothesis is true. If the null hypothesis is not true, then this is not the probability of observing a value of statistic that's at least as extreme as the one you actually observed. Now, what does this at least as extreme mean? Because clearly you could define that in different ways. The p-value that I defined in the previous slides is called a left-sided p-value. So a left-sided p-value is the probability that the test statistic is at least as small as actually observed if the null hypothesis is true. Okay. The probability the test statistic is at least as small as actually observed if the null hypothesis is true. And then you can probably guess what the other definition will be. The right-sided p-value is the probability that the test statistic is at least as large as actually observed, assuming that the null hypothesis is true. There's two more definitions. The one-sided p-value is equal to whichever one is smaller, the left or right-sided p-value. So if you find that the value actually observed is toward the left side, then the left-sided p-value is going to be smaller. And if it's toward the right-sided p-value is going to be smaller. The definition of the one-sided p-value is the minimum of the left-sided p-value and the right-sided p-value. And the definition of the two-sided p-value is 2 times the one-sided p-value. So what we're going to do is go back and actually calculate these for the HLAB example with the Bernoulli assumption. Okay. So the one that I was already calculating is the left-sided p-value. Right, what's the probability we would observe a value at least as far to the left as we actually observed? Well, of the 6 possible ways the randomization could come out, 3 of them were at least as far to the left as -0.5, which is the difference in means they actually observed. So the left-sided p-value is 3/6, which is a half. Okay. The right-sided p-value goes the other way. Let me write it with a different color because then we'll be able to draw it on the same picture. The right-sided p-value well, let's see, we actually observed -0.5, right? So that we always count that one. It's at least as extreme. Well, a half is bigger than -0.5 and 1 is bigger than -0.5. So I see 1, 2, 3, 4, 5 of the 6 cases where the difference in means would be at least as large as the one I actually observed if the null is true. Okay, so the right-sided p-value here is 5/6. Note that these don't add up to 1. They won't add up to 1 when you have very small cases like this one, where the fact that we're talking about at least as large or at least as small matters. But for most realistic cases, these two numbers essentially add up to 1 because it doesn't matter that you're double counting the one that you actually observed. Okay, what else? Well, the one-sided p-value is whichever one of the left and right is smaller. So the way to calculate a one-sided p-value is to calculate the left, calculate the right, and see which one is smaller. In this case, 1/2 is smaller, and I can see that by looking at the picture, the histogram, because you can see that -1/2 is toward the left side of the picture. So the probability you get a value at least as far to the left is going to be smaller, and the probability you observe something at least as great as what you observed. And the definition of the two-sided p-value is twice the one-sided p-value, which is just 1. Okay. So that's a hypothesis test. We have a null hypothesis. We have a test statistic. Using the fact that we know how the randomization was done, we come up with a reference distribution for that test statistic, and we come up with a p-value. Why do we do this? Well, it's just like the lady tasting tea. We do this because if the value we actually observed is very extreme compared to what we'd expect to see when the null is true, then perhaps the null is not true. So if your p-value is small, that suggests that what happened is would be pretty surprising if the null hypothesis is true. And perhaps if the p-value is small enough, you might decide, okay, I think the null is actually not true. Now, looking at this example, I don't think these p-values are particularly surprising at all, right? With this tiny little data set, right? Like looking at that left-sided p-value of 1/2. Am I surprised when something happens that would only happen 1/2 of the time? No, right? Something that would happen 50% of the time, I'm not surprised. Right-sided p-value, not surprised. If I look at the one-sided, the two-sided, none of these p-values are small. Now, of course, that's because I used a tiny data set. In fact, if you look at this, the smallest possible p-value, left-sided p-value you could get is 1/6. And I'm not actually even surprised when something happens that would happen 1/6 of the time. If I roll a die and get a 1, that has a 1/6 probability, but I don't find that to be particularly surprising, right? So actually, with this tiny little example that I've given you so that we can do it by hand, it's impossible to get a p-value so small that we would think maybe the null hypothesis isn't true. But of course, with a larger data set, you can get very small p-values. You can be way far to the left side or way far to the right side of a distribution. So you have the opportunity to get a value that is so extreme that it suggests perhaps the null hypothesis is not true. Now, what's the right cutoff? You've probably heard before that 0.05 is a popular cutoff for a p-value to be small enough that you would reject the null. There's nothing special about 0.05. Given that it's helpful to have some kind of cutoff, 0.05 is certainly a number that we can use, but there's nothing special about it, right? A long time ago, about 100 years ago, a statistician named Neyman was like, hey, we need a cutoff. How about 0.5? That's really it. Okay, there's nothing, no reason to it. It just becomes such a strong convention, and many people just blindly use that 0.05. But honestly, a data set that leads to a p-value just a little bit less than 0.05 and a data set that leads to a p-value just a little bit greater than 0.05 are only just a tiny bit different. Like maybe you made one small change. There's nothing special about 0.05. What I would rather have you do than use a strict 0.05 cutoff is look at the data, look at the context, look at the p-values, and decide whether you think that what actually happened, in this case, a difference of negative 0.5, would be surprising compared to what else could have happened. And in this case, I would say no. I would say that what we have here is not surprising. So what I will write here is if the p-value is small, perhaps we have reason to doubt the null hypothesis. And so people will say reject the null hypothesis. If the p-value is big, that suggests that what we observe is pretty typical of what would happen if the null was true, right? We can say there's no reason to doubt the null. Now that is not the same as knowing that the null is true, right? You saw in the previous case that we had big p-values because the sample size was really small, not because we were confirming that the null hypothesis was definitely true. So this does not mean that we prove the null, rather it means that we have no reason to doubt it. And sometimes people will say fail to reject the null. A common cutoff for accept versus reject is 0.05, but not for any reason. Okay. So it doesn't really matter to me what your cutoff is, because if you make you shouldn't be making decisions based on a strict cutoff anyway, in my view, right? You should be looking at the data as a whole. You should be visualizing the data, and getting a p-value is only one small tool that can help you decide, what the result of your data analysis is. But you can't just use a strict 0.05 cutoff. And in fact, if you're writing an academic paper, even at the college level, if you're writing a college paper, you should not be using terms like reject the null hypothesis or fail to reject the null hypothesis. You will not find academic papers that said, I did my psychology study and in the end, I failed to reject the null hypothesis. We don't use that language, right? Rather, people write about the context. And that's what I'll ask you to practice doing in this class, right? Rather, people say things like, I looked at my data and there's no reason to suspect that there's any difference between using intervention A versus intervention B, right? That's the kind of thing people would say. In parentheses, P equals, 0.27 or something. That's the kind of thing that you see. Another thing to mention here is a p-value, supposed to say less. less than 0.01 or maybe 0.001 is equivalent to 0. In other words, even though statistical software will print out p-values to several digits after the decimal, don't report that your p-value is 10 to the negative 27 or 10 to the negative 8. That doesn't matter. What people write is things like p is less than 0.001, and that's enough. Okay, there's nothing else that you need to write there.